RNNs are one of the approaches to deal with sequence input and sequence output. RNN stands for Recurrent Neural Network. We're going to start by looking at a general structure of a recurrent neural network, and then later we'll look at the actual implementation. So the idea of a recurrent neural network is we have a box that we feed in information at time steps. So here we feed in x sub I, time step 1, and then later on we're going to feed in x sub I at time step 2. And it's going to feed out y hat sub I. So, and then there is hidden state in here. So somehow we're going to maintain some state information within this RNN. For example, so we can feed in, let's say, at time step 1 for an example of, let's look at an example of the simplest example would be the Alexa. So we're going to feed in at time step 1 the sample at time step 1. So that'll go into the RNN. And then the output, which will be the yes or no, will come out. So this is going to be y hat sub 1. And this is going to be x sub 1, which is an audio sample. So we feed in an audio sample, we get it a 0 or 1. And then we go ahead and feed in the second audio sample and get out y hat sub 2. Feed in the third audio sample, get y hat sub 3, and so on. So we see pretty well how this can work with equal sequences. So sequence of size n to sequence of size n. We have x sub i's going to a corresponding y hat sub I. On the other hand, let's say we've got a one-to-many. So we have a single input, and we're going to go some sequence, okay, which is going to happen to be n. Right here, when we had our audio samples, we don't know exactly how long each sample is. Some samples are smaller, some samples are longer, but it is some sample of some size. And what the important part is that the output is of the same size. Here we're saying we do some input, and we're going to get some output of some size. We'll find out what it is. We don't know necessarily ahead of time. So what we're going to do is feed in our single input. Okay, so we feed in x sub 1. And x sub 1 is going to be, well, let's say in this case it's going to be our image. So we have as x sub 1 our image. However, an image really wouldn't be too good coming into the RNN. What we really want is some summary of that image. So what we're going to actually do is feed it through some CNN, perhaps a pre-trained CNN, where we'll take off the last non-convolutional layers. So we might just output the last convolutional layer, and that would be what would go in our x sub 1 here. X sub 2 and on would be empty. That is, we have to always in our RNN feed in some x sub I. And so in this particular case, we're going to go ahead and feed in a non-trivial x sub 1. That is, it's going to be the output of a CNN that then goes into here. And x sub 2, x sub 3, x sub 4, and so on are going to be empty. One thing to note as we're doing our training, we'll talk about training later, but our training here is going to be jointly training the RNN all the way back to the CNN, so that the CNN is going to learn what the RNN needs. Okay, so we can do some fine-tuning here of the CNN to fit the RNN's needs. So x2 and on are going to be empty. So what does that mean? The y sub i's now are going to be words. Of course, when we talk about words, we're never actually outputting text. We're instead going to be outputting some index into some dictionary. But that's what we're going to output here. And so here, y hat sub 1 equals, I'm going to say the first word. It's not really the first word. It's an index, and it's really a probability distribution for the first word. I think when we talked about the caption before, so maybe the caption is going to be, again, a pastoral meadow spits out this probability distribution. Y hat sub, so now as we go into x sub 2, it's really not fully empty. And the reason is we actually are going to, the RNN doesn't know what word is actually going to be generated. It provides a probability distribution for the first word. It's up to us to actually pick a word. So we've got a probability distribution. Maybe, for instance, the distribution is A is probability 0.3, and an is probability 0.2, and the is probability 0.2 as well. And then we've got a bunch of other words, all with different probabilities that sum to 1. It's up to us to decide which one to do. Maybe what we're going to do is we're going to just take the maximum. So that would be A. Maybe we're going to flip a coin. In this case, a three-sided coin, a 0.3, 0.2, 0.2, whatever the other probabilities are, coin. So we have a non-zero chance of choosing any one of these non-zero values. In any case, what we're now going to feed into this RNN for our sequence is the word that we actually chose to use. So this is common when you are generating sequences, in that it often will want to know if what the previous sample was. If we are outputting probability distributions, the RNN is going to need to know what was the previous word that was chosen. So we're going to actually feed in here, let's say we choose A. And upper lowercase don't really matter here, so ignore that for a moment. So x sub 2 is going to say, we have no image, we actually output an A. And x sub 1, we're going to actually have an image, and we'll also output, I don't know, some XX beginning of stream, just to say we're just starting. Once we output A for x sub 2, then we're going to go through the RNN. The RNN has a history, so it still remembers what it needed to about the image. Okay? So has history. Now it also knows that the first word that was output was A. So now y hat sub 2 is going to be the probability that we have sort of word 2 given the A was the first word. We get some probability distribution. All of the words that begin with a vowel are going to be very low probability because we don't have in English A and then a word followed by a vowel. But all the words with consonants would have higher probability because we can have A and something starting with a consonant. So you can see that's why the RNN needs to know for y hat sub 2 whether y hat sub 1 was A or N or the or something else. And then we will get this probability distribution. We'll again decide what word we want to use. And then we feed in for x sub 3, empty. And again, the word we actually chose. And when I say word here, I really mean the index of that word in the dictionary. So it might be a bucolic. We feed that in, we get out at y hat sub 3. This is the probability of, for all the words, the word 3 being the next word, given that the previous two words were A and bucolic. And that's how we continue, except how do we know when it's done, right? It keeps outputting these words, and then eventually it presumably decides that it's done. And the way that happens is that the dictionary would include also a possibility for XX, let's say end. Okay? And so for the very first word, this might have been 0.000001, very small. But when we get to, let's say, the fifth word, a bucolic, let's say a bucolic landscape with a man under a tree. So it has done those 9 words, and it may be then that y hat sub 10 has a very high XX end. Right? Maybe that's 0.4. And so once we have decided to do an XX end, then we're done in our iterative approach or looping approach of feeding in an x, getting out a y hat, feeding in an x, getting a y hat, feeding in an x, getting out a y hat, and so on. So eventually, in this particular kind of a case, we're going to get out a y hat which has a high enough xx end that we actually end up choosing it. And once we choose an xx end, we've decided that is the end of our generation of our output sequence. So this gives us a single to a sequence of n. How big is n? It depends on two things, right? It depends on the y's that are getting generated, and also depends on how we're actually using these probability distributions to choose, to decide that this is complete, right? To actually decide that this is a good time to be selecting the xx end from all of the probability distribution. Right? Maybe xx end is just going to be so large compared to any of the other values, right? This is going to be, 0.9959s, and these all are going to be some tiny epsilon, that it's very clear that xx end is over. Let's look at a many to one case. So here we're going to look at a Yelp review. We're going to look at a very short Yelp review. So let's say the review is, "It was good." So what we would feed in basically is that x1 would be, so we'd actually put in an x1 which was something like the beginning of the stream. So just to say it's at the beginning. x2 we could then say was it, x3 was, x4 good, and then x5 something to say that we're at the end. So maybe xx end. So that summarizes our three words here, and they're surrounded to show that we're at the end and at the beginning. And again, a reminder, these aren't the actual words because we can only send in to neural networks tensors. These are going to be indexes into our dictionary, probably one hot encoded. Our associated y hats, we don't care what y hat 1 is. We don't care what y hat 2 is. We don't care about y hat 3. We don't care about y hat 4. We do care about y hat 5. And y hat 5 would be the probability of a positive review. So during our training, for this particular case, we are just not going to care what the RNN spits out for all of the preliminary y hats. We only care about what the y hat is when we feed in an xx end. That is, when we say, this review is now over. Please tell me your result. Note the history here, right? The history is going to be the history of everything that has been input prior to this. So when we get, for instance, to xx end, we have previously entered all these, the beginning, it was good. The history of the RNN must be maintaining that somehow. Just like in the case where we did the captioning, the RNN knew we fed in the previous word we had just generated, and then it kept a history of any previous words. So anything that it has gotten as input, it can keep as part of its history. It can also keep output as part of its history, but in the case of generating text where it's this probability distribution, it needs this extra information. Is given this probability distribution, what did we choose to do with it outside of the neural network? All right, let's look at another case where we've got a sequence of one length, and we're going to output a sequence of a different length. And in this case, let's look at the translation again. So we would, in x1, say that we're the beginning of our, let's say, stream. x2 would be my, x3, name, x4 is, x5, Neil, x6, end. And this would now be the indication to the translator RNN, okay, now for you to start translating. So y1 hat is, we don't care. y2 hat, all the way to y6 hat, we just don't care about. We're not going to be looking at the outputs. They're not going to be part of our loss function. So since they're not part of our loss function, they're just not going to get trained. And now, actually, that's almost all the way to y6. So y5 is where we don't care. y6 hat is where we want the RNN to start providing our translation. So it's again going to give the probability of the first word. We are then going to use that probability distribution again to decide which of the words we want to generate. And then for x7, we're going to actually have x1 equals beginning of string, comma, empty, 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 and empty. Because our input consists of two things. What is our input and what is the word that has been generated. When we're not in the generation phase, right, this is often called decoding and encoding. So we can look at this kind of as a problem where we have some English and we decode it into some representation. And then from that representation, so this is a representation, we encode it back to some other language. So the decoding phase is this first phase where we're feeding in what the English is. And in that case, we don't care what's been output. Nothing has actually been output. And then in the encoding phase, so this is the decoder, encoder is often how that's written. Here, we have no input, and our output is going to be, let's say, may. Because we took a probability distribution over all these words. May was very high up there. We, let's say, were greedy and just chose the highest probability and ended up with may. So we feed may in, and now y hat 7 is the probability of W2 given that W1 equals may. X8, we don't care about the first thing. And then we're going to do YAMO because the probability of YAMO was very high. Y hat sub 8 is now going to be the probability of word 3 given that word 1 equals may and word 2 equals YAMO. Okay. Word 2 being YAMO, we have just put in, right? So we're just inputting YAMO into our RNN. And the may, it would have to remember that from the RNN in its history. X9, again, don't care. And then may YAMO, Neil. This assumes Neil is in the dictionary, and let's just assume that's the case. Y hat sub 9 equals the probability of W4, given W1 equals may, W2 equals YAMO, W3 equals Neil. And presumably, the probability is going to be quite high that this is the end of the translation. So we look, we see that the end is quite high probability. We're greedy, we just choose that, and then we know we're done. So that's how translation works, given that we have not talked at all about how this RNN actually works, right? Just the fact that it is a neural network and it has some history, and we know basically how to train now, and we know how to set up a loss function, right? We know that we will set up a loss function that, let's say we've got some paired English-Spanish translations. So let's say this is in English, my name is Neil, and we know that we have a training example whose output is may YAMO Neil. Then we know that we want to, our Y6, not Y hat, but our Y6 would actually be a one-hot encoded may, right? So may would be 1, everything else would be 0. And then our Y2 hat, our Y2, not hat, just Y2, would be the YAMO would be a 1 and everything else would be a 0. And then Neil would be a 1, everything else was 0. And then an end would be a 1 and everything else was 0. So that's how we're going to do our training. Maybe on we have multiple training examples. Sometimes we have the same English sentence translated differently. That's certainly a possibility. That's okay. The neural network can learn that, right? Sometimes we'll say the first word should be may. Sometimes we'll say the first word should be some other value. And eventually, we would imagine that the neural network is going to learn that it's a high probability that the first word is may, but there's other words that it could be as well. So the basics of what we've learned here is, given we have this black box of an RNN where we feed in an X at each time step and we get it a Y hat at each time step, how we can handle various kinds of problems involving sequences. So how we can handle a sequence that has a output for every input, how we can go from a single input to a sequence of output, how we can go from a sequence of input to a single output, or go from a sequence of inputs of one size to a sequence of outputs of a different size. And the key really in these sequences is almost always we're going to have a marker that this is the start of the sequence. We'll have the sequence, and then we'll have a marker that it is the end of the sequence. We'll talk in a later video about actually what's inside this black box, how an RNN works. And we'll also talk at a little more length of how we do this generation of text, okay, when we have probability distributions. Because although it's possible to just take the maximum, that would yield a situation with no stochasticity. So we'd have always the same text output, and that wouldn't be very good.